Hello, this topic will be on stresses on combined loading, and I will emphasize on Mohs circle and also shearing stress. Okay, because this example is very unique and requires quite a bit of analysis. Okay, so this example is a white beam. Okay, white or you call it white flange shaped beam, and it's loaded with the stresses as shown. Okay, and we have specified a beam to use, which is W241 by 41.7. We want to find the stresses at element A, and I also would like to do at element B. Okay, so the first thing we do, you look at our transformation, ensure that our transformation is the same as what's specified down here. Okay, so it's the same. So from here, I'm going to draw our global transformation. So we are aware that this is our point, this is our x-axis. Okay, given that this is our x-axis, and the other direction correspond to our y. So this is our y-axis. So defining your axis first is critical in solving a problem like that, because you're going to draw them in 3 view. So we know that over here, this is our z-axis. Right, so by looking at our table, which we'll refer quite a bit later on, so we know that our area is equal to 5320. Okay, depth is 205 millimeters, and so on. Okay, so this is critical. It's important to know which is your IXX and IYY, because this is a multi-axis loading. Okay, so there are two formulas that the general formula that we're going to use is stress in the Z direction is equal to P over A. So for this case, it's PZ over A. So that's why you know the area. Plus by moment about y-axis. Okay, so we're going to have moment about the y-axis over IYY multiplied by x plus by mx over IXX multiplied by y. So that's why it's critical to know where is your IYY and IXX. Okay, and then the other formula that we are going to apply is the shear stress will be equal to so we have shear stress in both direction. So Vx over Iyy, area about the first moment of area about the y-axis. So this is divided by t, and also it can be equal to Vy over Ixx, first moment of area about x-axis divided by t. So that's why it's critical to know where is your Ixx and Iyy and what they are. Okay, so we know that Ixx, so let's put down here. So Ixx is already known to us, which is equal to 40.8 times 10 to the power minus 6 meter to the power 4, and we are aware that Iyy will be equal to 9.03 times 10 to the power minus 6 meter to the power 4. So these two numbers are important. You mix them up, your analysis will be wrong. It's critical to know when to use what. Okay, so now let's break down our structure. Okay, into components into either X, Y, or Z component. Okay, so we're going to view now. So from here, we're going to view this structure on the XZ plane. Okay, so we're going to view this. So this is our X, Z, and this is our rotation in the Y-axis. So we draw our member. We can sketch this out. Okay, so it's fixed at the bottom. So like what I always elaborate is you have to draw your element. Okay, so I'm going to first draw the position on my neutral axis. Okay, so this is our neutral axis, and you sketch out your element. So 75. Okay, so this is our element. Sorry, so there is our element A, and this is our element B. Okay, so I'm going to call this EL B. Excuse me. And this one is our EL A, element A. Okay, so at a certain height, we have a load of 25 times 10 to the power 3. And then we have forces going twice. We have 2 forces. So 2 times by 8 times 10 to the power 3, or twice. Eight times 10 to the power 3. And then we have a vertical load coming down. We have a vertical load coming down, and it's coming out at 100 times 10 to the power 3 Newton. Okay, so that's all the load we have. So we know from here, from this diagram, acting down on the axis, neutral axis, in line with our axis, that would be our PZ, that would be our axial load. And you will induce a 1 minus 100 times 10 to the power 3 Newton. And this, you know, that is going to be compression. So I just put com. So you can say, now we can immediately declare that element A and element B will be under what? Compression. Okay. So that's why later on we need to know the area. Okay. So the next thing we can see, do not, okay, so like our standard practice, do not analyze. You do not analyze force vector that are either you see in dot or cross. Okay, don't analyze them. Okay. So in the next thing we're going to do, we know that we have shearing stress Vx. Right. So this Vx is twice times by 8 times 10 to the power 3. So the shearing stress, so shearing force will be 16 times 10 to the power 3 Newton, and it will go towards the left. Okay. So we know that the shearing stress will have values. Okay, so we know that for element A and element B on the shearing stress, the shear, from what we can see, right, is not the outermost, is not equal to 0. I'll elaborate on this later on, why it's not equal to 0. Okay. And then the last one that we can see is moment about y-axis. So we know that is when it's going to deform due to the moment about the y-axis. The deformation pattern is going to look like this. Okay. And this is due to the 2 times 8 times 10 to the power 3. Okay. So I'm going to declare like anti-clockwise going this way is going to be positive. So moment about y will be equal to twice 8 times 10 to the power 3. And the height to the element A is 0.6. So 0.5 plus 0.1 is 0.6. So you calculate this, get 2 times by about 3 times 0.6. You get 9,600 Newton meter. And for this, right, so better, this is important value. And we know that this will be going anti-clockwise. And we know from here, element A will be under compression, right, because it's rotating this way. And element A is on the left hand side of the neutral axis. And if we were to construct the moment of X, it's going to do this way. Sorry, moment about Y. So A is compression, head of the arrow. And then element B, due to this, will be under tensile. Okay, so do the analysis now. Later will be easier for you. So looking at over here, so we have PZ, right, VX, MY, and there's nothing more to analyze. Okay. Next, we're going to look at the YZ plane. So we're going to construct YZ plane. So this is our Z, this is our Y, and right hand rule, this is rotation about X. Okay, then we're going to construct the structure again. So you can sketch as much detail as you want. So for this case, I can see the 2 lines coming down here if I view it there. So if you guys I hope you guys will not get confused. And then we have the position of the neutral axis again. So this is the position of neutral axis. So we are going to draw the forces. So what we have is we have going the other way, going away. So this is 8 times 10 to the power 3 Newton. 8 times 10 to the power 3 Newton. And then we know that we are going to get a load down here. Okay, let me remove this first. We are aware that we're going to have a vertical load coming down here on one end. So this is about 100. It's not about, it is 100 times 10 to the power 3 Newton. And then we have a force and this force is going to be 25 times 10 to the power 3. Okay, then we draw our element. So over here will be our element B. And over here will be our element A. Okay, so we are going to look at Vy. Okay, we're going to look at Vy. So we know that Vy will have a load of 25 times 10 to the power 3 Newton. And we are also aware that at element A and element B, okay, the shear will not be equal to 0, which I'll also elaborate later. Okay. So the next one is we want to take moment about x. So I'm going to call this direction positive. Okay. So moment about x will be equal to 25 times 10 to the power 3 force. And then the distance is 0.5. Okay, so relative to the element, it's 0.5. The 100 relative to the neutral axis, right, is also, now for this you calculate to the neutral axis, not to element A, okay, because it's force multiplied by perpendicular distance. So from here we're going to plus 100 times 10 to the power 3, and we need to find what this distance now is. So this distance over here, then we go to our table. So the distance is 205 divided by 2. So this distance over here is 205 times 10 to the power minus 3 divided by 2. Okay. So this is multiplied by 205. So from here we will get power 3 times by 205 power minus 3 by 2. So 22750 Newton meter, and it's rotating this way. Now you guys will be confused, when do I actually, why that distance, why not to the element? Okay, so if you look at the 25 times 10 to the power 3, so moment is force multiplied by the perpendicular distance. So to the element over here, right, is of interest. The perpendicular distance is this distance, right? So this is the perpendicular distance, and this is where we get our 0.5. This force will not intersect the neutral axis. Okay, so you can not focus on the neutral axis, where our neutral axis is here. The other force, the 100, okay, the perpendicular distance will intersect the neutral axis. Okay, so once it intersects the neutral axis, you have to take that distance to the neutral axis. Whereas the 25 did not intersect the neutral axis, that's why you take the distance to the element. Okay, so when the perpendicular distance don't intersect the neutral axis, then this distance is between the element and applied force. Okay, to acquire the moment. Okay, so if the perpendicular distance, okay, so if the perpendicular distance intersects the neutral axis, Then this, I'm going to copy word for word over here, okay? Then this axis. Then this distance is between, this way change, okay? Is between the neutral axis and applied force to acquire the moment. Okay, so this one don't, and but it intersect. Okay, so this one is the distance is between the element and the applied force. If it intersect the neutral axis, okay, then it's between the neutral axis and the what? Applied force. Okay, so this is this part. I'll come back. So we have more or less completed our analysis. Oh, I forgot something. Okay, so from here we know that element A, right, will be under tension, and element B, the distance is pretty is as good as equal to what, 0, because it's on the neutral axis. So how this structure will deform, it will be doing this. Okay, that's why. So this is the moment about x-axis. Okay, I'll continue in part 2 of the lecture.